Okay, then I don't think I have anything else to say. So we're very happy to welcome Julian Sahasrabudhe from Cambridge, who's going to talk to us about counting zeros of cosine polynomials, a problem of Littlewood. So welcome, Julian.
All right. Thank you so much, Sean. This has been such a cool seminar. It's amazing that you guys have thrown it together so quickly, and it's gone really well. I've certainly been following it and enjoying it quite a bit. So thanks for doing that. The community's really benefited. All right, so today I'm going to talk about this problem, which is actually some work, it'll be mainly about some work that I did a few years ago now. But I thought I'd talk about it because it's not something that I've really presented to this community, and it's also something that I've revisited, or a different aspect of I've revisited with my co-author, Thomas Yuskevicius. So we'll get to that, but it'll be actually mainly focusing on some work I did a few years ago. So, all right, so let me introduce the main object of study for today. So the idea is I take a finite set of integers, and now I define a cosine polynomial, this f sub a, and just the sum of the cosines with the frequencies that lie in this set. Okay. And this is a very interesting object to me. There's certainly many questions and a bit of a history of these sorts of problems of studying polynomials with restricted coefficients. And really the question sort of, or to me, the meta question is, well, I have some constraints on this Fourier series here, right? Of course, I can write essentially any function in its Fourier series, okay, basically. And now I have some interesting restriction. And I'd like to say, okay, so what does that mean on the other side? What does that mean for the behavior of this function A? So there's many lovely results, Erdős, Turan, Sego, Poya, and certainly for us, the hero is Littlewood. So in 1968, which is quite late in his life, he actually publishes this kind of somewhat sporadic monograph, which is just a list of questions that seem like his personal questions that he's been holding on to for his life, his family problems, you might call them. And today we're going to talk about what's question number 22, which I've rephrased slightly here for the context. So just introduce this notation. What's the minimum number of zeros that this polynomial can have? And really, I mean minimum number of zeros in the period, 0 to pi, because of course this thing lives in 0 to 2 pi. So what's the minimum number of zeros in the period? And he actually offers up a somewhat bold conjecture or a guess at what the answer to this should be, which is possibly n-1 or not much less. So to get a feel for this question, I thought, okay, let's think about the most basic polynomial in a sense, which is a place that we often start, which is the random polynomial. So let's let this z of f be the number of zeros of f in 0 to pi. So f is just some function on 0 to pi. And okay, so I want my set, remember, to have size n. So let's just, seems like a good random model. Let's take a half random set in 2n, right? So now with high probability, we certainly have this, right? So it's basically n. And how many zeros does such a polynomial have? So interestingly, this is actually a very beautiful area in its own right. So what is the behavior of a random polynomial? And for this particular question, this theory certainly furnishes answers. So in particular, we know that the expected number of zeros of this guy is 4 over square root 3 times n, which I will point out is at least n-1 by quite a bit. Right, so this is random polynomials work. So let me just quickly mention that I've read this result off from, in particular, the work of Flachet, but lots of ideas in this proof are from Ibragimov and Maslova, and there's really a whole world here that I'm just scratching the surface. Oh, a pretty world. So, nice to mention. So here's another example, just to get going with this question, which comes from Fragility polynomials. So if P is congruent to 1 mod 4, it turns out that you can write the Fragility polynomial. It doesn't matter essentially what Fragility polynomial is, but I can define this polynomial here, okay, which is not particular to P being congruent to 1 mod 4, but okay. And this is when it's a Fragility polynomial. Okay, so it's a slight cheat, of course, because this is the Legendre symbol here, and it can take negative value, so plus minus 1, 0. But okay, still an allied question, and I thought I would get it in here. And it's known in this case that the number of zeros is quite close to n here, so between 1.02 times n and 1.01, 2 times n. Hopefully, yeah, very good. And this was this particular result was shown by Conray, Granville, Poonen, and Sanrajan. But for us, I think I just want to furnish it as another example. That's okay. We know the random has quite a few roots. Here's a pseudo-random polynomial in some sense. It's a bit of a cheat, but still has quite a few roots. Okay, so now let's think for a second about the opposite extreme, right? So what's the opposite of random? Arithmetic progression, most structured. So here I'm just choosing the arithmetic progression from 0 to n. I've called it dn because it's like the Dirichlet kernel, but tiny difference. But okay, so for here we actually have an explicit formula. Okay, nothing interesting happening, right? So I can just, it's a matter of expanding a geometric series and a bit of work, but I have this explicit formula for it. And we see, look at, so now the first term is giving me about n zeros. Oh, that was the second term, about n zeros. And now this guy is going to give me about n zeros. And so again, we have the number of zeros is something like 2n. Okay, so again, bigger than n minus 1. And I want to just quickly point out an important behavior and very different behavior in this particular polynomial, which is quite interesting, which is, you see, if x is close to 0, think x is large constant over n, say, this sign guy is incredibly small, right? So this is like going to be like 1 over n. So this whole thing is oscillating on the scale of like n. So around 0, right, around x is 0, we have these very violent oscillations, right? So these very extreme, big sign changes. Whereas far away from 0, x is equal to 0, they're very moderate, right? So they're just these little constant fluctuations that are giving us zeros. Okay, so you might think, all right, so we dealt with random, right? We dealt with structured. So Littlewood looks like he's correct. And interestingly, so I think it seems like it was a shock to people in the community. When Borwein, Erdei, Ferguson, and Lockhart, so I should say this was in 2008, I believe it appeared, who found polynomials with n terms, so cosine polynomials, n terms, with significantly fewer roots. So it's n to the 5/6, basically. Zeros in the period. So this definitely is ruining this n minus 1 or not much less guess of Littlewood. So that's certainly off the table. But there's another interesting thing that I'd like to point out about this particular construction is, first of all, that it's very conceptually simple and illustrates how fragile these sorts of polynomials are to some perturbations. So let me just throw down the example here. So they define these polynomials. Okay, let's define these polynomials f and m. Okay, and then what have I done? I've just taken constant 1 for the first n minus m terms. And then these last m terms, these are going to be random, where these epsilon k are random Bernoulli coin flips. Okay. And this m, I haven't told you what m is going to be like n to the 1/3. And that's their example. So to me, what's quite striking about this is you take a polynomial with a shitload of roots, you perturb just a tiny, tiny bit of it, and it dramatically changes the number of zeros, which is quite interesting and something that's very challenging when working with these things, because you say, great, I understand 99 polynomial, like I'm going to win. no, there could be some little bit that's fighting against you. So this illustrates the difficulty as well. I'm sort of falling into this funny land as the light shifts. Maybe I'll do that. All right. And this is a good moment to advertise some recent work of Thomas Yuskevicius and myself, where we actually showed that you can find polynomials with significantly fewer roots. So actually n to the 2/3. That's 5, 6 versus 2/3 here. And our proof goes by way of actually analyzing exactly the polynomial I showed to you and giving a sharp bound on the expected number of zeros of that polynomial. So it actually works in all ranges for all m, right? So this is degree m, and now I've tinkered with the first m randomly, the first m coefficients. And interestingly, we see this m kick in right away, which is one particular interesting facet of this. But this is also the sharp bound. So this is up to constants, the number of roots. And how do we get this? Of course, we just optimize. We choose the best m for this bound. Okay, so perhaps this suggests the conjecture 2 to the n to the 2/3 or not much less. So I definitely think, and hopefully I'll be able to say something more about this later, I think that this construction feels quite sharp in many aspects. Okay, possibly this we could reduce this power of log if you really wanted to, but it does feel quite sharp. But it's hard to really say anything because I haven't told you anything about the lower bound yet. And here's and really the first part of Littlewood's question, which is, okay, we want the lower bound on the minimum number of zeros of such a polynomial, right? So, which is, I'll just write like this. What can I put here? What can I put here? Okay, so it's not entirely trivial even to do the following thing. Okay, let's put 1. Can you just prove that there's at least one root in the period? So I think that there's a very simple proof of this, but I can't entirely remember it. So I think maybe this is a coffee time level problem, even to show this, which it shouldn't be a triviality in view of Littlewood's question. But in some sense, the first real serious question about the lower bound is, does the number go to infinity? Right. So Littlewood was extremely bold, hoping that you had a linear number of such roots. Does the number tend to infinity? So this conjecture seems to be somewhat folklore. I don't really know what the first appearance of it is. Certainly it's subsumed in a sense by Littlewood's question, but it certainly appears explicitly in the paper of Borwin, Erdely, Ferguson, and Lockhart. And it certainly appears in surveys and so on as well. So just does the number tend to infinity? So no rate at all. And the first sort of advance towards this, there's several advances, but one important advance towards this problem is the following theorem of Borwin and Erdely, which is the following. So I'll just describe it. So they say, okay, let's first take an infinite set of integers, and now say that you build up your set, so your A's, a sequence of these A's, by just adding from this infinite set, one at a time, right? So in some sense, there's this nice limit object to my sequence, right? I'm just adding terms to this formal power series. And in this case, they were able to show that the number of roots tends to infinity. So there's sort of two important remarks to make at this point. The first of which is this does not imply that the number of roots tends to infinity. These really are special subsequences because we're adding one at a time. We have some sort of target infinite set that we're going towards, some sort of limit object, this like limit power series. And the second important observation, which is kind of interesting, is that they actually don't have any explicit bound here. This is really, it tends to infinity is genuinely what they're proving, which to me is sort of interesting, just interesting characteristic of some of these things.
What do you mean by limit object? This is not just a truncation of a power series?
Yeah, exactly. But somehow that's like a nice, there is this power series. I could imagine it really as the real part of a power series on the unit circle, or truncated object. And this is somehow very, very useful. Yeah, I agree. It's not obvious how this simplifies things, but
if you had a sequence where the number of zeros was bounded, could you not just patch them all together? Go ahead.
No, right? So because you could have, it could be getting sparser and sparser, for example.
Oh, of course. Yeah. Sorry. Yeah.
For example, yeah.
Wait, if Borwein and Erdőly did provide like a explicit bound, wouldn't that show that the number of zeros goes to infinity for any set A?
Yeah. So okay. So yeah. So maybe if there was, it's a little unclear what comes here, right? So maybe it was like log n, but then a constant that depends on the sequence or something like that. So yeah, so maybe I do agree there might be some connection between those two observations. Yeah, that's a good point. But yeah, so this is not explicit at all. Any more questions at that point?
Yeah, one more quick one. So isn't the integral of f sub a n 0 over 0 to 2 pi?
Sorry, the integral?
Isn't the integral of f sub a n equal to 0 if you integrate from 0 to 2 pi?
So it's zero. It's either 0 or it's 1. So if it's 0, then you have one root for sure. If it's 1, you need to do something with still.
I see. Okay.
Yeah. Good question though. Yeah. Perfect. 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 Okay. So the main thing.
Can I ask one more question? Sorry.
Yeah, of course.
I'm a little confused. So Z of f sub an. F sub an is a particular polynomial, isn't it?
That's right.
And shouldn't there be a minimum or something of that sort?
I see. So this, sorry, this is a particular sequence of ANs, and this number tends to infinity as n goes to infinity. So for that particular trajectory, like along that particular sequence.
Okay.
So as I understand it, you fix one infinite sequence and you take the first n terms in that sequence, and then the claim is that the number of zeros of that polynomial should tend to infinity. Is that right?
Exactly. Yeah, so yeah, like the truncations of a sort of cosine, infinite cosine series or whatever, 0, 1 cosine series. Okay, so the main result I'd like to talk about today is a resolution of this conjecture. So a result of myself showing that the number of roots tends to infinity, and in fact, with this particular triple log rate. Yeah, so I'm hoping that I'll be able to sketch the main elements of this particular proof. And just for comparison, before we feel too good about ourselves, this is a little ways from the upper bound, right? So the upper bound n to the 2/3 was this new bound of Thomas and mine, Yuskiewicz's. And we have a triple log lower bound here, so a little ways. I should note that this 1/2 was subsequently improved by Erdőly to 1 later on, so that's why is what's happened here. And I should also say that the conjecture that this number just tends to infinity was also independently proved by Erdőly, but without any explicit rate. Okay, so that's the gap. It tends to infinity. How do you prove it? And to discuss the proof, I would like to sort of talk about what's the word? Sort of an obstacle that you come across quite quickly when thinking about this problem. And the obstacle is basically there exists cosine polynomials that look extremely similar, but have bounded number of roots. And in particular, and similarly, there actually exist sine polynomials that have bounded number of roots. So, so there exists sine, I'm not going to show you exactly the construction here, but there exists sine polynomials with a bounded number of roots. That's what I mean by few here. So 0, 1 sine polynomials with a bounded number of roots. Okay, so replace cosine with sine, and the story is different. And from this, if you think about these constructions and what's going on, you can actually construct cosine polynomials with a bounded number of roots. So here is an example of a cosine polynomial with a bounded number of roots in its period. And so now it seems perhaps like I've just given you a counterexample to the theorem that I've claimed to prove. But now let me notice that these are not 0, 1 cosine polynomials, but these coefficients lie in the following exotic set: 2, 0, minus 1, 1. Okay. So they look scarily similar to what we're dealing with, but are not the same. It's not the same. So somehow our proof has to filter out these examples. Okay, how do you know if you actually gave me this, how do I notice where in my proof do I set that to the side and continue proving just for 0, 1? And the main idea here is to use a structural theorem that will say, okay, if you haven't won by now, if you haven't shown that there's lots of zeros by now, then it means that you can write your polynomial in a sort of structured way that you'll be able to start feeling the difference between these two things. And I hopefully will be able to feel the difference between these in the next 10 minutes. So let's throw up this structural theorem. So this is really the heart of the paper, the new idea, or whatever you want to call it. So, okay, so this is the heart of the cosine bit. Okay, so I'm going to let R be a finite set. So this could be 0, 1 in our application, but notably applies just as well to polynomials that are 0, 2, 1, minus 1, 1. Applies just as well to sine polynomials. Oh, okay, it's a tiny adjustment for sine polynomials here, but. Okay, essentially just as well. Oh, it actually does. Okay, and now I'm going to write down my exponential polynomial. So f is just an exponential polynomial. And I'm just putting this fancy f hat business here. Okay, just some coefficients, whatever. And my only restriction on these is that they lie in this finite set. Okay, for example, 0, 1. All right. All right, so now comes the structural, my condition. And it says, okay, say I can find a polynomial p that is of bounded degree and correlates with this function f in a nice way. Okay, so let's write that down, or whatever. Okay, so if I have a polynomial p, any polynomial, it doesn't have to be 0, 1 coefficients or any, can be complex coefficients even. So I have some degree t and I have some epsilon. And if the integral of this thing around the unit circle is within a constant factor of the maximum it could possibly be, then this theorem is going to say you're in a very good situation. Okay, so this is my definition of what it means to be correlated, right? So if you integrate around the circle, your mass is as big as, like, constant proportion as big as you possibly could be. Okay. Then we have quite a bit of structure. So we can decompose my polynomial, f, my original dude, into this bounded number of pieces. So this L here is not going to depend on n, but only depend on this input information. A little bit like regularity or something. So in particular, we have this, I have this bound here on L. Okay, so a big number, but okay, fine. So it doesn't depend on n. It just depends on this degree and the set, which is 2 basically. Right, and each one of these bits are going to be hyperstructured. So every one of these bits is going to be supported on an interval. So I've basically taken some chunk of my coefficient sequence. And on that interval, this dude is going to be periodic with bounded period. So this pi is going to be bounded just in terms of the degree. Okay. Okay, so what does this say? If you have a polynomial f, and you have a bounded degree polynomial p, so f has these special coefficients, and if f correlates with p, then you have to have this super special structure. Okay. Okay, so now I've confused you a little bit perhaps by talking about something that has nothing to do with zeros. Where are the zeros? How does this say anything about zeros? And so that's where I'd like to start. So how do I get from something like this to saying something about zeros? And in particular, separating out these nasty cosine polynomial dudes. Okay. So if I only have, say I have a polynomial and it has d roots, right? Then I have these chunks, okay, where my polynomial, it's positive, negative, but it only switches d times. So I can build a polynomial. So this is actually an idea of, in the sequence paper of Borwein and Erdei, just take a polynomial that interpolates not interpolates, but goes through those zeros, right? And then what do I get? I get a polynomial. I can ask for a polynomial of bounded degree. So bounded in terms of the number of roots, quite happily. And I can guarantee that p times f is positive everywhere. Great. P times f positive means that I actually get my condition with epsilon equal to 1 in this case. All right, so now I'm going to happily apply my theorem and say, great, so now there's my f. It had not too many zeros. That means I have a special structure to it. It has a special structure. All right, so this is the point at which we need to separate out those weird sine dudes with our happy 0, 1 cosine polynomials. And we just give a reason why cosine polynomials have lots of zeros where those sine dudes don't necessarily. All right, so the reason actually here, so I'm just gonna sort of blab a little bit and we'll see how it goes. So each one of these fi's, so what are these? These are basically just like, you took f and you zoomed in on some chunk, some large chunk of the coefficient sequence. And I said, aha, I know lots about this chunk. The coefficients here are periodic with some bounded period. Okay, great. Now, since it's periodic, I can sort of think of this, I can sort of expand this modulo, like in terms of the Fourier characters, you know, the integers mod p or whatever, right? So if I can think about that as a function in modulo p, where p is the period. So expand it out into that basis, and there's going to be a constant term, right? So the constant 1 character, and then there's a bunch of other characters doing their thing and whirling around. The point, what's special about cosine polynomials that are just 0, 1 is they have a lot of mass on that constant term. And how do we know that? We just look at the polynomial at 0. Because a cosine polynomial, 0, 1 cosine polynomial at 0, is big. It has size n, right? Sum of 0 cosines. So what that means is, in all of these expansions of these fi's, there has to be a certain amount of mass on this constant term. Okay, and now we can simplify things by quite a bit. So I can find another polynomial f that will just, it's actually very simple just to write down, that will just average out all these oscillating terms, right? Just sum them over their period, they're gonna just oscillate out, and leaves us nothing with our happy constant terms. And I get something like this, okay? And the big win here is the degree of this polynomial is bounded, this d, sorry, this s is bounded, basically because the period was bounded, which means this, now I can basically just deal with the roots of this s times f, right? Because I've only introduced at most some bounded number of new roots. So we're happy enough to work with this dude. All right, so now I'm just going to quickly sketch how we run to the finish from here. So I mean, if you're already happy, feeling like, oh, okay, this is a nice, happy situation, you're correct. In some sense, it's just a bit of work. So let me just sort of sprint to the finish. So I'm just going to sort of chuck to the side all the garbage. There's going to be some small terms here that don't really do much or not very interesting for us. We're going to push it aside. And now, in the same way I wrote that arithmetic progression, that cosine series and arithmetic progression, I can write this dude as 1 over sine x over 2, right? So this guy, which is getting huge near 0, times this sine polynomial, this with only a few terms in it. Okay, so there's this funny 1/2 or whatever, but it's not such a problem. So and now all we need to do is show that this interior polynomial has a bunch of roots near 0. And this 1 over sine x is going to exaggerate those roots so much that it will overpower any badness that this e can do. Okay, so that's how we finish. So with a bit of work, we can say that the number of zeros of the SF thing is large. And hey, S had small degree, so that means we can get to the finish in this case. Okay, all right, so this result was good in the case that was useful, actually for proving something about zeros. It allowed us to separate out these two cases between weird sine polynomials and our cool 0, 1 polynomials. But how do we prove it? So I should ask if there's any questions at this point. Any questions where we are? Okay, feeling good. Okay. Was there a question in chat? Something blinked. Okay, maybe not. Okay.
Is there an obvious, I have a question. May I go ahead?
Yep.
Is there an obvious counterexample in case the coefficients are, say, positive integers instead of, so I think the example that you gave had a negative integer as well. Is there an obvious counterexample in case you just allow positive integers?
That's yeah. Sorry, there was more?
And you minimize over the sum of the coefficients or something of that sort.
Yeah, perfect question. So let's see. So in general, if you just have general integer coefficients, I do not know. So here, not bounded or anything. I'm not sure. That's a good question, actually. I think actually maybe it goes. Maybe it goes. In the case that actually maybe that's possible. In the case that you have just say 0, 1, 15 is your coefficient set. This argument also proves it in this case. So this is really the key, is that having f large at 0 is the crux, and that really separates these two cases. Yeah, so perfect question. Yeah, so there's a more general theorem that says that. I just didn't state it to derail. Okay.
Thanks.
Any more questions before I move on? All right, perfect. Okay, so now I'm going to move back to try to sketch. So we saw how to use this structural theorem. How do we actually prove it? And that's what I'd just like to sketch out of the next, well, to the end of the talk. And let me do so by introducing a very important theorem, an independently beautiful mathematics, which is the solution of Konyagan and McGehee, Pignot, and Smith to another conjecture of Littlewood. So I'll explain the conjecture of Littlewood in a second, but if you want to be tedious about it, okay, this is technically McGehee, Pignot, and Smith. This is their statement and this beautiful result from the 80s. Okay, so let me just talk us through this statement, and then I'll say what it has to do with Littlewood. So I have this trigonometric polynomial, like I've written here, And when you read what I've written here, I want to draw your attention to the fact that these KIs or KJs, I've selected them to be increasing, and I'm really sort of focusing on the support of my polynomial. So these are not just consecutive dudes, these are like my non-zero elements in this series, which is going to be a really crucial aspect of this, well, was for them a crucial and also will be for us a crucial aspect of this theorem. Okay, so I've sort of highlighted the non-zero terms. Then I get this beautiful lower bound on the L1 norm of my function, just in terms of these coefficients. Okay, with some logarithmic weighting. And so why this was a big deal when it came out in the 80s and 81 is so it was a solution to a conjecture of Littlewood about, again, 0-1 cosine polynomials, and in particular about the minimum L1 norm that such polynomials have. So Littlewood conjectured that the minimum was actually attained by arithmetic progressions. So it's exactly the same problem for us, but instead of zeros, minimizing zeros, I'm minimizing the L1 norm. So he said, okay, I have n terms. What's the smallest? How do I arrange them to make the L1 norm smallest? And his conjecture was, well, actually still is, that arithmetic progression is the worst. And if you think about what the L1 norm arithmetic progression is, it's log n. And this exactly shows that this conjecture is true. So up to a constant, the arithmetic progression minimizes the L1 norm. And it's still an open problem to determine the exact, beautiful open question. And this was proved independently and genuinely independently by Cognac and McGehee, Pigno, and Smith in 81. All right, so next I'd like to I'm going to take this, I'm going to take our condition and I'm going to sort of write down a line of equations or inequalities or whatever. And this inequality is really capturing the push and the pull kind of behind this theorem. So in some sense, it's just one line and we can already start feeling what's going on. So here it goes. So first recall that we have this dude, right? This inequality. That's great. And now I'm going to apply this L1 norm, McGehee, Pigno, and Smith to the right-hand side. Now to the left-hand side, there's a natural move here. We can apply Parseval. And the good news here is this P is bounded degree. So the left-hand side only depends on like D, or a bounded number of the coefficients of F. Okay, that sort of feels good intuitively already. So here we go. Here's the basic chain of inequalities. All right. So for the moment, I'd like to point out a few things. The first thing is, recall that we know very little about P. And in fact, the mystery of P, in some sense, is, that's sort of now our vision on what's hard about going forward. Is we can't say, P is just, okay, we know it has bounded degree. In fact, you can say a bit more, like we can control, we have upper bounds on these coefficients or whatever. But we don't know a lot about it, so keep that in mind. The second thing is, this left-hand side only depends on a few coefficients. So for now, let's just think of it. We need to be more subtle than this in reality, but let's just think of this as a bounded quantity. Say bounded in terms of the number of roots. Okay, something my condition is controlling. Okay. Now, let's sort of zoom in on the right-hand side and see what's going on here. So here's a description of what might be very nice, a very nice situation. Is you'd like to say, oh, wait a second, this P times F, maybe that only takes, values, a few different values, in which case I actually have quite a bit of control, right? A bounded control on the number of terms that can appear in this sequence. Otherwise, they would sum up and give something bigger than the left-hand side. But we really have no control over what this P is. It's just some crazy polynomial. And in principle, this P times F could be very small. And it's even if that p times f is like very small for like 0.1 proportion of this sequence, we have this stupid logarithmic averaging, right? So that means everything is, we've totally lost control of the rest of the sequence. Right, so this logarithmic averaging sort of is hiding the end of the sequence. And if you recall from the conclusion, we want to say a huge amount about the entire polynomial. So the idea to get around this is actually pretty simple to state. So imagine we had some polynomial q. I say well-behaved here, which seems very confusing, but we'll see. We just need a tiny bit more of this q. This is really the key property. Okay, we want to find this special polynomial q, and I want to jam it into this chain of inequalities here. Right, so I just want to jam it right into this PQF. I want to get a PQF in there. Okay, and I want it to have this special property that if it is if it's small, so the delta is just some threshold, some mysterious threshold I haven't told you about, but there's some threshold at which if this PQF is smaller than that threshold for a large number of values, then it's actually just 0. And what's very nice about that is these small values don't ruin my logarithmic averaging. Because remember the Littlewood conjecture, it says, it just jumps over values that are 0. And I can move that average to later. So this says, if you're misbehaving, actually you're 0. Wonderful, the logarithmic average doesn't hurt you. You jump over it. So let's just see in practice what I mean by that. Okay, so same sequence I had before, but now I've just aggressively chucked this q into this equation. So okay, I'm paying for it here with this infinity. Okay, whatever. Let's not worry about that. Let's say it's affordable. Okay, and now I apply this the bound on the L1 norm to this new guy. And now we look at the world from the point of view of this. Actually, things are quite nice. Because if I have either I have the lower bound of some threshold delta on each term, in which case I get like delta log n or whatever, or I'm going to have a bunch of guys in sequence that are smaller than the threshold, in which case I say, then you actually just had to be 0. So from this kind of reasoning, we can just conclude, this thing is just 0 for all but some sort of bounded number of values. Okay, this depends on delta, epsilon, whatever, but it's controlled number of values in terms of R. And in which case we're just done. Why? Okay, so I haven't said why. This is a very nice situation to be in. I have a sequence, and I have these polynomials p and q, and when I multiply p and q by f, I essentially kill everything. Everything is very sparse polynomial. Okay, so let's zoom in on one of those long sequences where it's all 0, 0, 0, 0, 0, 0. Okay, what does that mean? So okay, this takes all a bit of work, right? But this basically means since f, this means that f sort of locally is satisfying a recurrence relation. So this PQ sort of looks like multiplied by 0. It means you're like look like you satisfy a recurrence relation in this interval. Okay, but f has coefficients only 0 and 1. So how do you satisfy a recurrence relation you're only 0 and 1? Well, you have to be periodic. So that's how you reach the finish of expanding in terms of these periodic functions. Okay, so that was if we can find this fancy q. So are there any questions about that? So this is the finish with the dream after assuming we have this dream q.
Sorry, Julian, can you explain the conclusion once again? How did that happen?
Yeah, of course, yeah. So the idea is, okay, so I think this maybe the hat is a little bit confusing. Just forget everything. And now I have a polynomial that's very, very, very large, right? Very, very large. And now I have this PQ, which are a small degree, bounded degree. And I multiply f by p times q. And now I get, what this says is that I have a polynomial that's, the resulting polynomial is very sparse, very few non-zero terms. So let's zoom into like a long interval. So there's only a bounded number of non-zero terms. There's going to be like a long interval, right? Like 1 over n over this value, this mysterious big O value, for which we're 0 in that entire range. And the idea is that locally, these coefficients look like they satisfy a recurrence relation defined by PQ. So you can just sort of, if you like write down what that means to be 0, you say, those actually just, the coefficients of f are satisfying a recurrence relation locally. And then what you want to say is, okay, you think really hard, okay, what 0, 1 polynomial satisfies a recurrence relation? The only things are periodic. And then this is how we get to our conclusion, that f is, okay, so now I need to apply this to all the possible intervals. Okay, there's some possible discard piles, but then I just make a new f that's a single element or something. But yeah, I basically chunked up the polynomial into these bits. So this is right. So was that maybe a bit more helpful? Or?
Yep, thank you.
Cheers. Yeah. Okay. Thanks for asking. Right. Aha. Perfect.
Sorry, can I, sorry for being slow, but what is, like, what all of you just said have to do with the inequality? Like, how are you using the inequality for the L1 norm?
Right, good question. So I'm assuming that this Q has this fancy property that if it's small in absolute value for a large number of values, then you're 0. So what that means is, if I put it into this inequality, so I mean, I guess the question one needs to ask himself is, how could this thing not sort of be large?
Oh, sorry, on the previous, you were choosing Q, so that, can you go back one slide?
Yeah, of course, yeah. Too many slides, there we go. Yeah, so Q is this polynomial that has this property that if you're small, for a bunch of consecutive values, a bunch of consecutive r's, then you're 0.
And you got this independent of the inequality?
Sorry, at the moment I'm just assuming that we've found this Q, and just describing how to get to the finish, assuming we have the Q. I've said nothing about how to find it yet.
Okay, thanks.
Okay, perfect. Yeah, thank you very much for your question.
Is the point, sorry, this very stupid question. The left-hand side of this inequality, that is bounded, is it?
Yeah, for example, it's bounded, yeah. We need to be a little bit more tricky than just, so let me just note the extra degree of trickiness here is my choice of P, the scaling didn't really matter. So it could be that your enemy chose something that was like confusingly small or confusingly large, this P. Okay, but so this needs to come in some point. But I think it's good just to think of it as medium size, and this is just bounded. Yeah. Any more questions?
I'm a bit confused with the range of R. So here you are asking Q to behave in such a way for every R in this large intervals. But then in the next slide, you were saying that something was holding for a different range of R. So do you just put it in chunks? So you just cut chunks of
exactly,
like omega
yeah.
RD. I see.
Yeah, so you sort of zoom in on a chunk, you deal with that, move it aside, and then continue. Yeah.
I see.
Right.
Okay, thank you. Mm-hmm.
Okay. Yeah, thanks for your question. Okay. So, perfect. Okay, so now we need to find this Q, right? That's the trouble, finding the Q. And it turns out, let's look at the theorem again. If you sort of stare hard enough at this theorem, or maybe look at it in a blurry way, it's sort of clear what Q should be. So let me just sort of phrase this statement in terms of what we've already seen, which is the following, which is the only thing that can really screw, if this theorem is true, the only thing that can really screw you up is if F is a sum of periodic guys with bounded period, right? This is, if you know the theorem is true, how you have to prove it is the offending dudes have to be these periodic guys. So you want to find a Q, right? We want to find a Q that's going to stomp on those periodic guys. So this is a bit fast, but just read this as the annoying thing on that right-hand side, a few slides back. Let me just, whoops. The annoying thing that can happen on this right-hand side is if F was one of these periodic, sums of periodic guys. Okay. And when you think about that, you say, what I need to do is kill periodic things. And then you write down this polynomial. Okay, so this d to the 1 plus little o1, let's not worry too much about this. The important thing is to look at one product. What is the analogous word of summand? It's product and anyway. So look at one of these guys I'm taking a product of, right? What is this doing? So when I multiply a polynomial by that 1 minus e to the I x k business, that's exactly killing, okay, except for a bit of noise, killing all the bits that are periodic with period k. Okay, so let's just, if these things are really going to satisfy the conclusion, well, we know what we need to do. We need to knock out all those bad things, which are all the guys that are periodic with period up to some amount. And that's actually the choice. Okay, so showing it actually works. I do not know. When are we going to, Sean?
6-ish, but
6-ish.
don't feel too constrained by that. People will leave and they'll catch up on YouTube if they need to. So. Okay,
so maybe I'll be a bit meaner than I would be in a seminar, and a bit less polite. So we'll sketch how this Q is the right option. So we had some sort of hazy view that like these FIs were the offending guys. This Q is killing the guys that are there. So let's prove it. Let's sketch the proof. Okay. All right, so to sketch it, we're going to assume, of course, that we have, so we're looking at an interval. So I'm looking at a long interval. Okay, long just means a large constant. I shouldn't have wrote this weird notation. I don't know why I did that. Anyway, this long interval, and there's this mysterious threshold, which I haven't told you what it is exactly, but it's some small number. Okay, great. And now I'm going to introduce a little definition, which is actually extremely natural. So I'm looking at this sequence, right, which will ultimately be a chunk of a polynomial related to my polynomial. And I'm going to find the space of k windows to be what? So it's just going to be, I take this chunk and I look at all k segments of length k in this chunk, right? So those give me some vectors, each of length k. And now grab all those vectors and throw them in a vector space and take the span. Okay, so this is sort of like okay, yeah, so we look at the span of all of these k windows. And that's going to be the space of k windows. And I'm going to break up into two cases based on this. Okay, and I'm going to say some, yeah. All right, so the case one is when the space of windows has full rank. Right, so this is this mn, this is the piece of my polynomial that I'm zooming in on. Okay, it has some size. And for reason, it's a little bit confusing. So this Q I've invited into this F here, but we'll see why. So important aspect. Okay, so the space of D windows has full rank. And the other case, of course, is that it doesn't have full rank. Okay, so let's deal with the full rank case first. And to prove this, I'm just going to sort of stare at this a little bit longer and hopefully convince you of what's going on. So this might be a little bit fast, but hopefully it rings some bells at least. So now, for a bunch of R, so for R in, oh, maybe I was a bit, I shouldn't have this bracket inside here. Just this PQF guy is small for R in this, this range. Now, this thing, this Q times F, has full rank. So now I'd like to think of this Q times F as a matrix, a linear operator or whatever, that's sort of acting on P to get these coefficients. And what this at most delta says is that Q times F, this operator, when it hits P, it gives you something small. It gives you a small vector. Okay, so, but we know that the space of windows has full rank. And moreover, Q times F is special. It actually is an integer polynomial with bounded coefficients. You can think about that for a second. Which means the smallest eigendirection is bounded away from 0 by some concrete amount. So by some, you can do this, for example, by applying Kramer's theorem or something like that. So you can bound this minimum eigendirection away from 0, which means I can get a which means if P is small when I hit it with Q times F, actually P itself had to be small to begin with. But remember, we had this quantity here. So forget about the right-hand side for a second. We had this quantity here, and that was sort of holding everything in balance. That was our friend on the left-hand side, holding everything in balance. And if P is small, then it means this whole quantity is small. And if you choose delta correctly, you can ultimately get a contradiction from this. Okay, it just means that you're sort of hitting, you're basically choosing what scale or what delta should be here. Okay, so the idea is here, if this has full rank, we can bound sort of the smallest possible push that this operator has on P, and then that allows us to turn it around and say something about the left-hand side. Okay, the case 2 is more interesting. So what if the space of D windows of this thing does not have full rank? Okay. Okay, so in this case, okay, so this thing doesn't have full rank. What this means basically, if the interval is long enough, again, that locally your coefficients satisfy a linear recurrence relation. So you have to be a little bit careful. We need to work in a finite interval, so it's a little bit of linear algebra, but not too hard. But basically things are behaving the same. Okay, but we know that also that Q times F has bounded coefficients, right? So each one of these is just some integer in some finite range, bounded by D. To say it's at most D, at least minus D. Not quite true, but it doesn't matter, so bounded. So if the interval is long enough, I can expand it in terms of a bunch of TIs, which are periodic. So now I can actually expand these coefficients, this QF, in terms of periodic guys. Okay. Okay, so this seems similar to what we want, but it's not quite there. What we need to do is now apply Q again, right? So we want Q to be this annihilator. We should kill stuff with it. So let's apply Q again to this. And we exactly arranged Q to kill periodic guys. Okay, so I'm not really doing any bookkeeping here, but you can assume that that works out. So this guy is actually, there should be a hat here, excuse me. There should be hats. Hats here and here. But this is basically killing all these periodic sequences. So now we have this equation. Okay, that's not very interesting until you think a little bit about what Q is. So Q, if you think Q sort of is a linear operator acting on F, it's actually an idempotent linear operator. So this, the second equation, left hand of the second equation, is equal to this. In which case we get this Q times F is equal to 0. in a slightly smaller interval again. In which case we're at the finish line because, again, I can just multiply by p and I get this, and again, in a slightly smaller interval. I just lose possibly some noise on the ends of my interval, and I'm done. Okay, so, okay, so that sort of concludes the sketch of the proof. But the idea is basically there's two main cases for showing that Q works. So we kind of knew what Q had to be, guessing from what the theorem said, sort of hoping the theorem was true. There's the one case when we have full rank of these subsequences. And there's another case where we don't have full rank, but that allows us to get a little bit of information about what's going on. And we chose Q to have some good luck also on this side. Okay. So just a little summary of the proof. Right, so we cared a lot about what was going on, right, about this sort of sum. So we analyzed this particular sum, and we wanted to have this particular jump property. Okay, either it's at least delta or it's 0. And we found this fancy Q that really that satisfied this property. And now we could use this beautiful result of McGeehee, Pigno, and Smith. Oh, there's another GE there. To relate this to this main statement in our structural results. Okay, and then we also sort of sketched how, given the structural result, we could ultimately deduce this particular lower bound on the number of zeros. Okay. I didn't say anything about the quantitative aspect of it, but this is what comes out. Okay, so just to finish up here, I'd like to just phrase the structural result as applied to the problem of zeros in a kind of, to me, is sort of a surprising way. So, so it actually says something about trigonometric polynomials with few zeros. So if you remember back to those misbehaving polynomials that we saw before with few zeros, they actually had quite a bit of this periodic structure. And a corollary to our structural theorem, it says that this is actually no mistake. This is no coincidence. That really, if I have a real trigonometric polynomial with at most k zeros, so a bounded number of zeros, and coefficients in a finite set of integers, then f has this very particular structure. Okay, so you can break it into these L bits, L bounded, by just in terms of k and r, and each of these FIs have this structural property. So looking at this, clearly it applies to polynomials, for example, of this form, right? So these are like they're called reciprocal Littlewood polynomials, so, another kind of polynomial I'm very interested in. And interestingly, so certainly it gives you quite a bit of information about what polynomials like this have with few roots, but amazingly, I wasn't able to resolve the following conjecture. So this is not really sure what the origin of this problem is. There's certainly some papers written on it, referring to it as been around at least. But just the same question for plus minus 1 coefficients. Right, so this theorem says you have a huge amount of information about what it looks like. Can you just go the final distance? So it's a bit strange that 0, 1 is fine. 0, 1, minus 1, and 2, dead. Plus 1, minus 1, open problem. Okay. So I just want to close by reminding you of this, what I hope I've convinced you is a pretty question of Littlewood, who asked for the lower bound of the number of real zeros of these polynomials, and remind you of the current state of the art on it. So I think I'll end there.
Thank you, Julian. I think we should all unmute and thank Julian for a nice talk.